Hey guys, Stover here with video 2 for today, okay? And this should be it, okay? So for today's lecture is just going to be these two videos, okay? So this is video number 2, this is it. I'm going to pick up on this because some of you may already be annoyed at this point because you're thinking, are you freaking kidding me? Why are we using the quadratic formula in a chemistry class? This is obnoxious. Why can't we not use this? So I want you to look at this previous example, okay? What about this is screwing you over? Is having just the x squared on the top the problem? How can we get rid of an x squared? Right, yeah, we can just take a square root. So having an x squared by itself is not a problem. It's having just the number with the x. That's the problem. It's this. It's this. It's the fact that I have these negative x's here on the bottom that I'm multiplying together, and it's this fact that I'm going to end up, even if there was only one thing here on the bottom, you would still have to distribute this number, and you would end up with the number times x. That's what's screwing you over. It's the negative x. Okay? So now, thinking about that, what was the value of k for this question? So I'm going to jump forward. The value of k for this question was 50.5. Now, k is relatively close to 1, but it is larger than 1, which means this is a product-favored equation, which means it is proceeding to the right. And this negative does make a substantial difference against the initial concentration. But what if k was really itty-bitty? Like, what if k was a super small number, like times 10 to the negative 3, or times 10 to the negative 4, times 10 to the negative 5, something like that, right? If k was that small, then it's not really proceeding that far to the right, which means this x that we would have calculated using the quadratic is not going to make that much of a difference compared to the initial concentrations. So, what this means is that we can introduce an approximation, okay? So basically, when your equilibrium constant is so small, then the position of the equilibrium is favoring the reactants, and this negative x is not really going to make that big of a difference, which means we can choose to ignore it. Now, in life, when we make assumptions, we have to always sort of double check our assumptions and make sure that they are correct, which we will also do that when we finish the example problem. We will check it and make sure that it is an okay assumption to make, okay? But we're going to make an assumption, okay? And that assumption we make is that the negative x is so small that we can consider it irrelevant, and we can assume that the equilibrium concentration of the reactant is the same as the initial concentration of the reactant. Now, we know better, but we're going to assume that they're the same to simplify our math, to simplify the amount of work that we're going to have to do. Okay? Now, if k was really big, you could make the opposite assumptions, but don't worry about that. I'm not going to ask you a question like this. All the questions I'm going to ask you are going to be when k is super small. Right? So let's look at an example. So for the equilibrium shown in the slide, I2 going to make 2I. Kc is 3.76 times 10 to the negative 5. So 0.0000376. Small number, which means this is not proceeding very far to the right at all. This is a reactant-favored equilibrium, which is good because that means we can make some approximations here. If 1 mole of iodine, I2, is placed in a 2-liter flask and heated, what will the equilibrium concentrations be? All right, so now we're going to go to the handy-dandy piece of paper here, and we're going to work this sucker out. All right, so first things first, we need to write down the equation, okay? So we have 2, sorry, I'm doing it wrong already. We have I2 goes to make 2I. Okay? ICE. Now, initial concentrations, you should know all those. It tells you that we have, so the molarity of I2, it tells me that I have 1 mole in a 2-liter flask. So the molarity then would have to be a half, right, for I2. So we can put that in up here. So it's going to be 0.5. They didn't tell me an initial concentration of my product, which means I assume 0. Now the next step would be to write my changes, which since I don't know any equilibrium concentrations, that can't be a number. It has to be a variable. So this is a reactant, which means I started with something. So it's going to be negative, negative, no coefficient, so just negative x. All right, this is a product. I'm starting with nothing, so I'm making it positive 2x, right, where the 2 is coming from the coefficient. All right. Now, equilibrium, I plus C equals E. So 0.5 minus x, and then this is going to be 2x. All right, so I write my Kc expression. Always write the expression first. So this is I squared divided by I2. I know that this is equal to 3.76 times 10 to the negative 5. And if I plug in, I get 2x squared divided by 0.5 minus x. And here again, here's our problem, right? Our problem is this. Our problem is when I go to multiply and distribute this into this parentheses, I'm going to end up with a number times x. And I'm getting an x squared up here, which means I have to solve the quadratic. But because k is much less than 1, the equilibrium is reactant favored, which means x compared to the 0.5 molar initial concentration is considered irrelevant, which means I can do that. Math just got a lot simpler, right? So this is going to end up being 2x squared is equal to 3.76 times 10 to the negative 5 times 0.5. Okay, so 2x squared is 4x squared is equal to, let's get our calculator, so 3.76 e to the negative 5 times 0.5, and I get 1.88 times 10 to the negative 5. All right, next up, we need to divide both by 4. So if I now take that number and divide it by 4, I get 4.70 times 10 to the negative 6. And the last thing I need to do is take the square root. Okay? So square root of that answer, and I get I want to hold on to 3 sig figs, so 2.17 times 10 to the negative 3 molar. All right, that's my value of x. So then, how do I figure out my equilibrium concentrations? Well, we're going to take this, and we're going to bring it back up to our ice table. So this then becomes 0.5 minus 2.17 times 10 to the negative 3. And this becomes 2 times 2.17 times 10 to the negative 3. All right? So then 0.5 minus 0.00217 is, in 3 sig figs, the concentration of I2 should be 0.498 molar. And the concentration of I is going to be 0.00217 times 2. So it's going to be double that. So 4.34 times 10 to the negative 3 molar. And that is the correct answer. That should be what appears on your slide. But remember how I told you that we made an assumption and we need to confirm that our assumption is accurate? How we're going to do that is to check your assumption. What you're going to do is you're going to take your x and you're going to divide it by your initial concentration of your substance. So I'm going to call this I2 initial, and we're going to multiply by 100. So in this case, our x was 2.17 times 10 to the negative 3. We're going to divide that by our initial concentration we started with, which was 0.5, and we're going to multiply by 100. And we need a number less than 5%. You need a number less than 5% for this to be accurate. So if we take this and we say 0.00217 divided by 0.5 times 100, we get 0.434%. That is less than 5% error, which means this approximation was valid. There is nothing wrong with what we have done with making the approximation, and we just answered this question without using the quadratic formula. Okay? Now, your homework has you answer questions using the quadratic formula. I am not for sure if I'm going to have you use the quadratic on your test or not. I will let you know on Monday. Okay? I'm going to think about that. I'm going to make your test over the weekend. But remember that your test on chapters 14 and 15 is going to be Wednesday. Okay? And this is going to be on that test. I'll make my final decision about if I'm going to have you solve the quadratic or not. But I guarantee you there will be something like this if you don't have to solve the quadratic. Basically, perhaps you could use the approximation to get around solving the quadratic. But again, I will be clearer with you when we get to that. All right, so that's it for today's lecture. The final lecture on Monday for chapter 15 is going to be on Le Chatelier's principle. Okay, so we will do this on Monday. We will also start a little bit of chapter 16, but that will not be on your exam Wednesday. Your exam Wednesday will just be chapters 14 and 15. Okay, and it's going to be administered through my LSMSA just like your quizzes have been. All right, so that's it for today. Stover out.